This explains why astronauts on the ISS, that's an abbreviation for the International Space Station, float. I've showed you all a couple of videos from astronauts on the International Space Station. Please don't think that they float because there's no gravity. That's a bad assumption. What holds the moon in place around the Earth? Starts with letter G. If Earth's gravity can reach all the way out to the moon, I assure you it can reach to the International Space Station, which is way, way, way closer. In fact, you can calculate little g on the ISS. It's not 9.8, it's about 9.2. They have almost the same gravity as on Earth. So Peyton, then the question is, why are the astronauts floating if there's plenty of gravity up there? It's not that there's no gravity, it's that there is no they, Mason, don't feel the ground pushing up on them. If they're sitting in a chair, they don't feel the chair pushing up on them. So another word for gravity is know now. So another word for gravity is weight. And in physics, another word for the normal force, how hard you feel the chair pushing up on you when you're sitting on it, how hard you feel the ground pushing up through your feet when you're standing, we call that your apparent weight. Your true weight is mg. But what all of you think of is your weight is actually how hard the ground is pushing up. That's why, Tristan, when you piggyback someone, you feel twice as heavy. Your mass hasn't changed. The ground pushing up through your feet, though, is having to cancel out your mg and whoever you're piggybacking, mg. So the astronauts are floating not because there's no gravity, but because there's no normal force. In other words, as a number, the apparent weight, the normal force of the astronauts is equal to exactly what number? 0. So a better question to ask is not why do the astronauts float? A better question to ask is why is there no normal force? And I said, hint, see F above on the previous page. Good, you actually looked. Example F, it's an elevator question, right? What? Tristan, candy for you. Loud and proud. Why are the astronauts floating? Say it. They're in free fall. This was Einstein's happiest thought. We talked about this when he realized that an object in free fall will not feel gravity. So the better question, Henry, is not why do the astronauts float? A better question, Peyton, is, well, if the International Space Station is in free fall, why doesn't it crash into the Earth? That's a better question. So, why is there no normal force? They are in free fall. Free fall. Bill Nye, I think. Why is there no normal force? They're in free fall. So how the heck can you be in free fall, falling, and not smash into the Earth? This was Isaac Newton's idea back in 1690. He published a paper. This is one of the many reasons, Chase, that we say Isaac Newton's one of the biggies. Put your pencils down, look up. Isaac Newton said, take the Earth. I'm going to change colors. Let's do it in blue, Mr. Dueck. Erase. So here's the Earth. And imagine we have on the Earth a giant mountain. And let's put a giant cannon on the mountain. Let's fire a cannonball. Boom. What if I put more gunpowder in? How will the cannonball travel? Shorter or further? Be stupid obvious. He said, boom. What if I put more gunpowder in? Boom. He said, it seems to me that there's just the right amount of gunpowder so that when I fire it, boom, it's always falling to the Earth, but I gave it just the right sideways velocity so that the Earth is curving away from it at exactly the same rate that it's falling. That's how you can be in continuous free fall and never hit the Earth. We have a name for this. That's an orbit. This was his proposal back in 1690, before we even had hot air balloons, let alone spacecrafts. I think this would work. Now, why doesn't this work near the Earth's surface? Why does this work better further from the Earth? Not because of weak gravity. What would make this so tough near the Earth's surface? So, go above the highest mountain, still couldn't be done very well. It's a major problem with anything when we try and go fast near the Earth. Air resistance. Well, where would this work then? Where there's no air. Where is there no air? This works great in outer space. This is why, by the way, if you watch a rocket launch, they will launch vertically, but watch them after about 30 seconds, their roll maneuver starts. They've got to get some serious sideways velocity so that they can fall down, but have the right sideways velocity so that the Earth curves away from them, so they always miss the Earth. That's what an orbit is. The ISS isn't in a complete vacuum. There's a tiny bit of air up there. That's why they have to do a boost every so often. I showed you all a video a few days ago of a boost. But yeah, works great. Works great. Stuff, if you put it up there, especially if you put it way up there where the air is so thin as to be negligible, it'll stay up there forever. Easy peasy. You can do something similar on the Earth here. You can get weightlessness by being in a jet airplane. There are jet airplanes that you can rent that will go up and then they will dive down at 9.8 meters per second squared, and you'll get about 20 seconds of fake weightlessness. It'll be like you're in deep outer space. In fact, NASA has a training jet that they use. They train the astronauts. Does anybody know the nickname that the astronauts give this training jet? It's called the Vomit Comet, because you're going to puke. Because here's the problem. You go 20 seconds of weightlessness, and then pulling up, you're pulling 2 Gs. And then 20 seconds of weightlessness, and then pulling up, you're pulling... And your body just doesn't like it. But it's still so cool, because you're getting 20 seconds to fly. You have your vomit bag, and you got a smile on your face, and you puke. Bring it on! I'm flying! I'm floating. You can also do this if you're not an astronaut. You can charter companies that do this. Put your pencils down, look up. A few years ago, the music band OK Go did this. So they're flying level, and then what they're going to do is they're going to dive down at 9.8 meters per second squared. They'll have about 20 seconds of weightlessness, and then they're going to freeze. The camera's going to stop recording. They're going to pull up and then start to dive down again and resume their positions. And they'll stitch it all together and morph it together with technology. But none of this is green screen or wires. I'll let you know when they're diving down. You'll be able to tell when there's no gravity. Sorry, when they're in free fall. So right now, level flight. Diving down.
Upside down and inside out, and you can feel it. Upside down and inside out, and you can feel it. Don't know where your eyes are, but they're not doing what you said. Don't know where your mind is, baby, but you're better off without.
Kind of thump into the seat. That was right when they started to pull up. Now they all froze in their position, pulled up at 2 Gs, and now, Peyton, diving down.
Inside down and upside out, and you can feel it. Don't stop, can't stop until you feel it going down. I wish I had said the things you thought that I had said. Gravity's just a habit that you bring.
Up, down. That was right when they started to pull up. Gravity kicked in. I got to be careful. Gravity didn't kick in again. Normal force kicked in again. Diving down.
You can't break. So when you met the new you, were you scared? Were you cold? Were you kind? Yeah, when you met the new you, did someone die inside?
Yeah.
Don't stop, can't stop, it's like a freight train. Don't stop, can't stop until you feel it going down. Don't know where your eyes are, but they're not doing what you said. Don't know where your mind Looks like it's time to decide. Are you here? Are you now? Is this it? All of those selves that you tried, wasn't one of them good enough? Cause you're upside down and inside out, and you can feel it. Inside down and upside out.
Bit of gravity, and then diving down again.
Don't stop, can't stop, it's like a freight train. Don't stop, can't stop till you feel it going down. I wish I had said the things you thought that I had said. Gravity's just a habit that you're pretty sure you can't break. Upside down and inside out, and you can feel it. Don't stop, can't stop until you feel it going down. Upside down and inside out, and you can feel it. Don't stop, can't stop until you feel it going down.
Little backstory here. This took them 20 times to do, 20 takes. And by the 20th, they thought they had it. 3 of them were doing okay. The guy in the red was throwing up like crazy. In fact, if I rewind it just a couple of seconds, if you look at it through the whole video, you can see he's sucking down air, trying to keep from throwing up. He was not enjoying this, but he knew the video was going to be good. So the 20th take, they thought they nailed it. They got down on the ground, they watched the video, and the first colored balloon that had popped, the paint had covered the camera lens for the rest of it. So you can find video footage of this guy sitting on the ground, I mean, just looking sicker than a dog, swearing at his friends as they're begging him, we got to do one more take, we got to go up one more time. And he finally, okay, I'm doing one more. Doesn't work, I'm quit, I'm done. He was throwing up like crazy. So what you saw was take number 21, where everything came together. But this was not easy, but great physics. Why are they floating? Was it because there's no gravity chase? It's because no normal force in free fall. You can charter those, by the way. They're about $5,000, $4,000. It's on my bucket list. I'd love to try that. I would happily be throwing up everywhere just to try all that stuff. I think it'd be so cool. Example 5. I like example 5. I like example 5. I like example 5. Example 5 is a nice question. A 55-kilogram person is standing on a bathroom scale while inside an elevator. What is the magnitude and the direction of the elevator's acceleration if the scale reads blah, 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 blah? Okay. Maddie, what's this question asking us to find? Keep reading. Keep reading. It wants me to find acceleration. Specifically, it wants me to find the magnitude, size of the acceleration, and the direction, because acceleration is a vector. You know what this is going to be a good job for? Let's do a free body diagram. Let's represent this person with a dot right there. What are the forces acting on them? Get the obvious one. Which way? What else? Well, you notice this person is standing on a bathroom scale. What's that physics code for? Which force am I talking about? What does a bathroom scale measure? Normal force. Which way? Up. Bigger, smaller, or the same size as gravity? Now that's the tricky part. Wait a minute. What's this person's mass according to the question at the beginning in kilograms? What's the scale saying their mass is? Are they feeling heavier? Or are they feeling lighter? If you're feeling lighter, which way are you accelerating? You're in partial free fall, down. So we're accelerating down. That means the shorter arrow is going to be pointing up. I'll make it stupid obvious. And I'll label that normal force. Now I can see how this fits together. Who's winning? Losing? Equals what? If I wanted to get the normal force by itself, I'd do a swappy dance, but that's not what they asked me to find. They want me to find A. How would I get the A by itself? Did I name this one after Tristan? No, who did I name this one after? No, Leo. Is it Leo's theorem? Leo's theorem. Or who did I name it after? How do we get the A by itself? I would have named it after somebody. Yeah, Leo's theorem. How do I get the A by itself, Leo? How to move the M over. Yeah, even though the left side is more complicated, right side still going to be divided by M. I'm going to go like this. Boom. Whole thing by M. Thought it was Leo's theorem. Back to you, Maddie. What's M? 45. Scales don't measure mass. They're wrong. 45. What's G? You've probably memorized it out of laziness. Minus problem. What's that 32? What are the units next to that 32? Well, that can't be the normal force, because if it was a force, what would it be measured in? Newtons. How do I convert kilograms to newtons? Zainab, you were kind of right, I think. I saw you typing on your calculator, maybe. No? Okay. It's not divide by 9.8. If I want to convert a force to kilograms, it's divide by 9.8. If I want to go from kilograms to newtons, it's times by 9.8. Yeah. So if you give me a scale reading in kilograms, the way scales work, Chase, is they're measuring the normal force, but when they actually calibrated it on there, they divided it by 10. That's kilogram. But 9.8. That's kilograms. So if I want to convert kilograms back to newtons, of course it's that, because Peyton, the units that we developed were on Earth's gravity. It's not a coincidence that it's a 9.8. It's because when we started defining force and how big a Newton was, gravity was baked into it because we were doing it on Earth's gravitational field. Divided by, Maddie, what's the mass? Yes, not 32. So all of you want to get your calculators out. Is this a fraction? Yeah. Use your fancy schmancy fraction button if you got it. Or, Ethan, you and I, brackets around the top, right? $45 times 9.8 minus 32 times 9.8, close bracket, divided by 45. I know it's going to be less than 9.8 because we're not in free fall. 2.83, and then the 1 repeats. Yeah. That's the magnitude. Units, Maddie? And then it did ask for the direction. Look at our free body diagram. Clearly, what's the direction of the acceleration? Yep. Well done. B, kind of similar. It still wants us to find the acceleration, magnitude, and direction. Henry, you know what this is a good job for? You don't say. What are the forces acting on this person? Get the obvious one. Which way? Down. What else? Well, they're standing on a scale. What's that physics code for a normal force? Which way? Bigger? Small? How you know bigger? Feels heavier. By the way, if you're on the elevator, this is what you will notice. If you're riding the elevator at Playland this summer, on the way up, you will feel heavier. If you could sit on a scale and if you glanced at it, you would notice, oh, it's showing more than my mass. And on the way down, you do feel lighter. But that's why the way down is probably scarier for most of you. Because you feel lighter, you feel like you're about to fly off the chair. You're not, but you feel like it because it's just not an experience we have much of. Heavier, we have lots of experience. Anytime we're piggybacking or even anytime you're carrying something, you feel heavier. There's not many situations where you just feel lighter all of a sudden. So I agree with you. Normal force is bigger. I'll make it stupid obvious. Henry, who's winning? Losing? Equals what? What am I trying to find? A Leo's theorem. Right? And then now, plug and shut. Oh, I don't know the normal force, but I know the scale in kilograms. How do I convert kilograms to newtons? It's going to be 64 times 9.8 minus M, 45, times 9.8 divided by 45, not 64. You know what? I might be able to just backspace and edit. That's a 64. Aha. That's a 45, and I already got the 9.8s in place and the 45 on the bottom. Henry, did you get 4.14 if I round off properly? 4.13, and then the 7s repeat, right? You all know, even though your calculator makes that last one on 8, it's actually 7 repeating forever and ever and ever. And some of your calculators might have a repeating sign that shows up. The newer software does that. Is that right, Henry? 4.14? Okay. Units. Direction. Yep. So for elevator questions, Peyton, I can either, like in this question, give you the mass and the scale reading, find A. Or, like the previous ones we did last day, I can give you A and one of the forces, find the other one, usually the normal force. What's your homework? So I had already assigned 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can also do all of part 2, question, or section B, question 1, section B, question 2. But first, I got one short video to show you. Put your pencils down, look up.